Hello, this is Jerry Lopez, and my topic is linear dependence and independence. So here's some topics that I'll go over briefly before the problem. So here we have matrix form, where we can have these sets of equations and turn them into matrix form, and we just multiply these columns by the rows to get this answer. So here a1 times x, a1 times x plus b1 times y, and we can do that for each equation. And then we have row reduction. So here's without row reduction, just traditional without matrix form. We have 2x plus 4y equals 6 and x plus 4y equals 2, and we just subtract the equations and get the answers, plug in and solve for y. But with matrix form, we can turn these sets of equations into this. And then row reduce. So what I did, I subtracted the first row by the second row, and then I subtracted the second row by the first row of what we got in the previous row reduction. And then lastly, I would divide the second row by 4, and then we'd get the following matrix, where we have 4 and negative 1/2, similar to what we got above. And then linear dependence and independence. Essentially, our sets of equations are linearly dependent if they have a linear combination, while independent equations are not. I'll explain this more in the example. So here we have problem 20 from chapter 3.8. We are given this set of homogeneous equations, which we can turn into matrix form. Then we row reduce. Feel free to pause throughout the video. So I subtract row 2 by row 1, then multiply row 3 by 2. Then I multiply row 1 by 4 and subtract row 4 by row 3. Then subtract row 3 by row 1 and add row 2 to row 4. Then I divide row 1 by 4 and then multiply row 2 by 2. Then subtract row 3 by row 2, and lastly divide row 2 by 14. You get this matrix. So here we can see the rank is 2 because we have 2 non-zero rows, and we can see that the matrix, or the set of equations, are linearly dependent. So we convert back to our original form of the equations, and we get x plus 2y minus z equals 0, and then negative y plus z equals 0. So we can solve and get y equals z and x equals negative z, and get the following solution. So this is important because we can use this for data analysis of data arrays. We can see the relationships between large sets of data, and linear algebra makes it extremely more efficient, especially with computers, and this is how we write code for programs to analyze data. And you will see more of this in computational physics here at San Jose State. So it is a very helpful tool for data analysis.